Welcome back to the Deep Dive. Today we're unpacking a concept that's quietly becoming the superpower behind truly effective AI. If you've ever felt, overwhelmed by the sheer volume of information an AI might be dealing with, or just wondered how to get one to really understand what you want, well, this deep dive is definitely for you. We're going to give you a shortcut, sort of, to understanding a really critical skill in AI, context engineering. Okay, so let's unpack this a bit. You've probably heard of prompt engineering, right? Everyone's talked about that. But today, we're going beyond that. We're talking about something broader, deeper, and frankly, way more impactful. Context engineering. For this deep dive, we've been looking at a whole stack of fascinating sources. We've got insights from AI folks like Andrej Karpathy and Simon Willison, plus perspectives from leading frameworks like LangChain and Llama Index and research groups like DR.ai. They're all kind of shaping this frontier. Our mission today is pretty clear. We want to equip you with a solid grasp of what context engineering actually is, why it's absolutely crucial for these AI agents everyone's buzzing about. And then, this is where it gets really interesting, we'll get into the practical stuff, the specific strategies people are actually using today, and even how certain frameworks are being built specifically to help you master this, basically focusing on the things to try here.
Yeah, what's fascinating is just how much the thinking has evolved. It's really not just about the words you type in a prompt anymore. It's about the whole ecosystem of information an AI sees and manages. So we'll be looking at this art and science from a few different angles, hopefully giving you those aha moments that turn a fuzzy idea into something you can actually use.
Okay, so let's start right at the beginning then. What is context engineering at its core? I know Andrej Karpathy had a great analogy.
He really did. It helps clarify things a lot. Think of the LLM, the language model itself, as the CPU of an operating system.
Right, the brain.
Kind of, yeah. And its context window, that limited space where the model actually sees the information it's working with.
Yeah.
That's like the RAM, the computer's working memory.
Okay, RAM. Limited space. Got it.
Exactly. And if we connect that to the bigger picture, just like your computer's RAM, an LLM's context window has a finite capacity. It can only hold so much. Context engineering, then, is sort of like the operating system's job. It's carefully deciding, what fits into the CPU's RAM right now. Karpathy calls it the delicate art and science of filling the context window with just the right information for the next step. It's about optimizing all the information you give it in that precious window.
It does sound a lot like prompt engineering, doesn't it? So for anyone still thinking, okay, isn't this just fancy prompting? How would you clarify that distinction, make sure we see the bigger scope?
Yeah, that's a really important question. How is it different? Well, prompt engineering, it really focused on crafting those clever instructions, usually in a single text string, right? Context engineering puts a lot more focus on filling that entire context window with the most relevant information, period. Doesn't matter where it comes from. It definitely includes prompt engineering as like a subset of techniques.
Right.
But it's fundamentally about building a whole dynamic system,
Yeah.
a system that intelligently provides the right info, the right tools in the right format, exactly when needed.
So when we talk about context,
Mhm.
what kinds of information are we actually talking about loading into that RAM? What fits?
Right, so we can break it down. Our sources point to several key types. You've got your instructions, which, yeah, that's your traditional prompts.
Yeah.
But it also includes things like memories, maybe few-shot examples to guide the behavior, descriptions of tools the AI can use.
Okay.
Then there's knowledge, actual facts, maybe other memories it has stored or information it pulls, like from a knowledge base.
Retrieval, yeah.
Exactly. And critically, tools. Not just saying, here's a calculator tool, but the description of how to use it, and crucially, the feedback or the results you get back when the agent uses that tool. That result is context, too.
Right. The output of the tool call itself.
Precisely. And beyond those big three, you're also looking at things like, obviously, the user's input, short-term memory like the chat history, maybe long-term memory across sessions, structured outputs from previous steps. Even potentially a global state or context for really complex agents.
Okay, that makes sense. And this whole idea of limited memory, limited RAM, and needing to carefully curate what goes in, that seems especially critical when we talk about AI agents. Why is managing this context their number one job? What are the real stakes if they get it wrong?
It's absolutely crucial for agents because, think about it, they're designed for these long-running complex tasks, right?
Yeah.
They're constantly going back and forth. They talk to the LLM, then the LLM says, use this tool. It uses the tool, gets a result. That goes back into the context, and it talks to the LLM again.
Rinse and repeat.
Exactly. And each interaction, each tool call, it just adds more stuff, more tokens into that working memory, that context window. And if you don't manage that context diligently, well, that memory quickly becomes this chaotic mess. It gets filled with irrelevant details, maybe conflicting instructions, or just too much stuff for the model to process efficiently.
So it's not just about speed then.
Oh, definitely not just speed. It directly hits the accuracy, the reliability, basically whether the agent can actually do the complex thing you asked it to do over time. They just accumulate a huge number of tokens very quickly otherwise.
And when that context window gets messy or overloaded, what are the specific problems we actually see? How does it fail?
Yeah, Drew Brunig outlines some really good categories for these problems with longer unmanaged context. First, there's context poisoning. This is nasty. It's when a hallucination or just plain wrong information slips into the context window.
Like a bad memory.
Kind of. Think of it like planting one false memory in someone's head. It can subtly corrupt everything that comes after. It leads to completely unexpected, often really bad outputs. it's it's a silent killer for agent reliability.
Okay.
Then there's context distraction. Simpler, maybe. The sheer volume of stuff just overwhelms the model. It can't figure out what's actually important.
Is it too much noise?
Exactly. Then context confusion, where some extra, maybe irrelevant context actually influences the response in a way you totally didn't intend, throws it off course.
Right.
And finally, context clash. This happens when different parts of the context window actually contradict each other. Maybe an old instruction conflicts with a new one, leads to inconsistent or just nonsensical behavior.
Wow, yeah, it really does sound like a minefield. Given all those potential traps, it's no surprise that folks at Cognition and Anthropic have basically said context engineering is effectively the #1 job for engineers building these agents.
Right.
Okay, so we get the what and the why. Now let's get into the practical how. Our deep dive pointed to 4 kind of core strategies that seem essential for anyone actually building these agents. These are the practical things to try, right? If you're building agents or even just thinking about them.
Exactly. The sources tend to group them into these 4 buckets: write, select, compress, and isolate. They're common patterns, really effective ones that you see in a lot of the popular agents out there today.
All right, let's take those one by one. First up, writing context. What does that actually mean for an agent? Why write it?
So, writing context is essentially giving the agent the ability to save information outside of its immediate working memory, its context window, like taking notes.
Oh, like a notepad.
Precisely. Just like we humans jot down ideas or summaries so we don't forget, agents are getting this ability. 2 main ways this shows up. First, Scratchpads. These are usually for saving information within a single task. A really good example came from Anthropic's multi-agent researcher work. The main agent, the lead researcher, would save its plan to a separate memory space, basically a Scratchpad,
Why do that?
to make sure the plan didn't get lost or truncated if the main context window got too full later on. Scratchpads can be pretty simple, like just a tool call that writes to a file, or maybe specific fields in some kind of runtime state object.
Okay, temporary notes for the current job. What's the other type?
Memories. Unlike Scratchpads, these are meant for remembering things across many sessions. Long-term stuff. I've seen some cool innovation here. Reflection agents introduce self-generated memories, kind of learning from past mistakes. Generative agents synthesize memories over time, building up a history. And now you see it in products people use. Things like ChatGPT, Cursor, Windsurf. They can auto-generate these long-term memories based on your interactions, trying to remember preferences or past conversations.
Okay, so you write stuff down, either short-term Scratchpad or long-term memory, but then you need to get it back when it's relevant. Right. That brings us to the second strategy, selecting context. How does that work?
Exactly. Writing it is half the battle. Selecting context is about dynamically pulling only the right relevant information back into the context window precisely when it's needed for the next step.
And how do you select from those Scratchpads or memories?
Well, reading from a Scratchpad might be a simple tool call, or maybe the system just exposes that part of the state directly. For memories, especially long-term ones, the real challenge is picking out the relevant ones. You might have tons of memories stored.
Right. How do you find the right needle in the haystack?
It depends on the type of memory. Maybe you're selecting few-shot examples. Those are like episodic memories of past successful actions. Or perhaps instructions, which are more like procedural memories. Or facts, semantic memories. Sometimes it's simple. Some agents always pull a specific file. Like Claude Code apparently uses a file called kiloue.md for its core instructions.
Okay. fixed context.
But for bigger collections, especially facts or general knowledge, that's where techniques like embeddings come in. You create these numerical fingerprints for pieces of text.
Right, vector search.
Exactly, allows semantic similarity search. Or knowledge graphs, which store relationships between pieces of information, those help index and retrieve the relevant bits efficiently.
Now, I remember you mentioning, or maybe it was Simon Willison, something about memory selection going wrong. Are there pitfalls here?
Oh, absolutely. Simon Willison shared this really striking example. ChatGPT, using its memory feature, unexpectedly injected his personal location, which it had presumably stored from a previous chat, into a request he made for an image generation.
Oh.
Yeah. Made him feel, as he put it, like the context window no longer belongs to them. It just highlights how incredibly precise this selection needs to be, and how context, if not managed really carefully, can surprise you in not always good ways.
Yikes. Okay, so selecting from memory needs care. What about selecting tools? You mentioned agents can have lots of tools.
Yeah, another selection challenge. If an agent has dozens or even hundreds of possible tools, just listing them all in the context window eats up space and can confuse the LLM, especially if tool description sounds similar.
So what's the fix?
A really powerful solution is applying retrieval augmented generation, RAG, but on the tool descriptions themselves.
Using RAG pick the tool?
Exactly. Instead of putting all tools in context, you use array to search the tool descriptions based on the current task, retrieve only the top few most relevant tools, and put those in the context window for the LLM to choose from.
Clever. Does it work?
Apparently, yes. Studies have shown this can improve the accuracy of the LLM picking the right tool by up to 3 times. It's a big deal.
Wow. Okay, and then the big one for selection. Knowledge, using array generally.
Right. Array is really a central challenge, maybe the central challenge, in context engineering for agents that need external knowledge. Code agents, agents that write or understand code, offer some great real-world examples here because code is complex. Varun from Windsurf, for instance, highlighted just how complex it gets. It's not just about, indexing chunks of code.
What else is involved?
It's using advanced techniques like AST parsing. That means analyzing the underlying structure of the code, its grammar, not just the text, to do what's called semantic chunking. Grouping code based on what it does, its meaning. Then combining that with embedding search for finding conceptually similar code, plus traditional search like grep for finding exact text matches, and maybe knowledge graphs to understand how different code parts relate.
That sounds intense.
It is. And then, after you retrieve all these potential pieces of context, there's a crucial final step: re-ranking. You need another mechanism, maybe another model, to look at everything you retrieved and put the absolute most relevant snippets right at the top so they have the best chance of influencing the LLM correctly in that limited context window.
Wow. Okay, selection is clearly a deep topic. That brings us to the third pillar, compressing context. Given that limited window, this seems vital. How do you keep things lean?
Absolutely vital. Compressing context is all about retaining only the essential tokens, the necessary information for the task at hand, and discarding the rest to save space.
What are the main ways to do that?
A really common approach, especially for long agent interactions, is context summarization.
Just telling the LLM to summarize the past.
Kind of, yeah. Claude Code, for example, apparently autocompacts. When the conversation history gets close to the context limit, it automatically summarizes the whole user-agent interaction up to that point. This summarization can be recursive, like summarizing summaries, or maybe hierarchical.
And can you apply summarization at specific points too?
Definitely. You don't have to wait until the window is full. You could summarize, say, the output of a tool call if it was really long and wordy, just keeping the key results. Or summarize the state of one agent before handing off information to another agent in a multi-agent system, reducing the token load during that handoff.
Smart. What's the other main compression technique?
Context trimming or pruning. This is more about actively filtering or just cutting out parts of the context.
How does that work?
It can be simple heuristics like, always remove the oldest messages once you hit a certain number. Just keep the most recent conversation turns.
Okay, straightforward.
Or it can be more sophisticated. You could use train models, actual context pruners, that learn which parts of the context are less likely to be important for the next step. The Provence system for question answering was an example of this. It learned what context to keep and what to prune for that specific task.
But wait, are there situations where trimming too aggressively or even summarizing could actually hurt? Like, what if you accidentally cut out a subtle but crucial detail from way back in the conversation? How do engineers balance that?
That's an excellent point, and it's a constant, delicate balancing act. Over-trimming or poor summarization can absolutely lead to the agent getting amnesia, forgetting something vital it knew earlier.
So how do you know?
This is where evaluation becomes absolutely critical. You need robust tests, regression tests, specific scenario tests to check if your compression strategies are actually helping overall performance, or if they're inadvertently losing key information in some cases. Often, something like hierarchical summarization, where you roll up details into higher level summaries instead of just deleting them, might be safer than naive trimming because it tries to preserve more of the conceptual understanding. But yeah, it's a trade-off you have to measure.
Okay, that makes sense. Measure, measure, measure. All right, final pillar. Isolating context. How does splitting things up help?
Isolating context is about strategically partitioning information. You're trying to help the agent focus on specific aspects of a problem without being distracted or overwhelmed by everything else that might be floating around.
And how do you achieve that isolation?
One of the most popular ways we're seeing right now is through multi-agent architectures.
Breaking the problem down for different agents.
Exactly. You create specialized subagents. Each one handles a specific part of the overall task. And critically, each subagent gets its own separate context window, its own set of relevant tools, its own specific instructions.
Like the Anthropic researcher example again.
Precisely. They found that having multiple agents, each with its own isolated, focused context, often outperformed just one big agent trying to juggle everything in a single massive context window.
Why is that better?
Because each subagent can really dedicate its limited context RAM to its narrow subtask. They can explore different facets of the problem in parallel without interfering with each other's working memory.
Makes sense. What are the downsides?
Well, challenges definitely include potentially higher overall token usage across all the agents combined, and the added complexity of coordinating these agents, making sure they communicate effectively and hand off work properly.
Okay, multi-agents is one way. What else?
Another interesting approach is context isolation using environments, sometimes called sandboxes.
Sandboxes, like for security.
Partly, but here it's also for context management. Hugging Face's Deep Researcher agent provides a cool example. Their code agents generate code, right? But that code gets executed in an isolated sandbox environment.
Okay.
Now, the key is only select information from that sandbox, like maybe just the final return value, or a success failure message gets passed back into the LLM's main context window. This effectively isolates potentially huge token-heavy objects that might be generated or processed in the sandbox, like images, audio files, large data structures, keeping them out of the LLM's primary working memory.
Ah, so the messy stuff stays contained.
Exactly, and that state within the sandbox can even persist across turns, so the agent can continue working within that isolated environment if needed, without polluting its main context.
Need any other isolation techniques?
One more subtle but powerful way is using runtime state objects. Think of the internal memory or state that the agent orchestration system maintains. If you design the schema, the structure of that state object carefully, with different fields for different types of information, you can store context coming back from tool calls or intermediate results in very specific fields. Then you only expose the contents of a particular field to the LLM when that specific piece of information is explicitly required for the next decision. It's like having different labeled compartments in the agent's brain and only opening the relevant one when needed.
Got it. Compartmentalization.
Basically, yeah. Keeps things tidy and focused.
Okay, so these 4 pillars, right? Select, compress, isolate, give us a great strategic map. But for the engineers listening, the real question is, how do we actually do this? What tools and frameworks are out there that are specifically built to help manage this context juggling act? Our sources mentioned LangGraph and Langsmith specifically.
Yeah, absolutely. But before we dive into LangGraph features, it's really important to flag 2 foundational pieces that you absolutely need no matter what framework you use for effective context engineering.
Okay, what are they?
First, observability and tracing. You have to be able to see what's going on. Where are the tokens going? What exactly went into the LLM prompt at step 3? What did that tool return? Tools like Langsmith are really strong here. They excel at agent tracing, giving you that visibility into every step, every tool call, the exact prompts. You simply cannot optimize context if you can't see it clearly.
Right, can't fix what you can't see. What's the second piece?
Evaluation. You make a change, you implement a summarization strategy, you try REG-based tool selection. How do you know if it actually helped or if it made things worse in some subtle way? You need robust evaluation. Langsmith also has capabilities for agent evaluation, letting you run tests and compare performance before and after your context engineering changes. If you're not measuring, you're just guessing.
Crucial point.
Mm.
Observability and evaluation first.
Mm.
Okay. With those in mind, how does a framework like LangGraph then make implementing these context strategies easier or more controllable?
So LangGraph is designed as a pretty low-level orchestration framework. That means it gives you a ton of control over the flow and, importantly, the context. You define your agent essentially as a graph, a collection of nodes representing steps or functions and edges representing the flow between them. You write the logic inside each node. This graph structure lets you very precisely control what context is available and what gets passed along at every single step. So let's see how it helps with our 4 strategies.
Okay, let's start with writing context. How does LangGraph help there?
For writing context, Scratchpads are almost built in. LangGraph has this central state object that automatically gets checkpointed and passed between the nodes in your graph. So any node can easily write notes, intermediate results, or anything else to the state object, and it's readily available to any future node in that execution. Perfect for Scratchpad.
Okay, that sounds convenient.
And for long-term memory, it's treated as a first-class component. You can easily configure and access memory stores within any node, reading or writing context that needs to persist across different runs or sessions. There are even abstractions like LangMem available to make managing different kinds of memory easier.
Nice. Okay, what about selecting context?
For selecting context in LangGraph, because you define the logic in each node, you have really fine-grained control. A node can specifically pull only certain parts of that central state object, selecting just the pieces of context relevant for its specific job. The long-term memory components integrate well, supporting different retrieval strategies. You can fetch specific files or do embedding-based retrieval over collections of documents or past memories. There are even dedicated tools emerging, like the LangGraph Big Tool Library, which is specifically designed for doing that semantic search over tool descriptions we talked about earlier, selecting relevant tools dynamically.
RG for tools built in.
Yeah, or at least easier to integrate. And more generally, because LangGraph is low-level and graph-based, it's super flexible for implementing all sorts of complex ARGAC strategies. There are quite a few tutorials out there showing different ways to build ARG pipelines within LangGraph.
Good to know. How about compressing context?
For compressing context, LangGraph offers some built-in utilities, particularly for managing chat message history, things like summarizing it or trimming it automatically when it approaches context limits.
So some standard stuff is handled.
Right. But beyond that, because you control the nodes, you can easily add custom compression logic wherever you need it. You could have a specific node whose only job is to take the output of a verbose tool call and summarize it before adding it to the state.
Okay.
Or you could insert summarization steps at specific phases of your agent's process, maybe after a planning phase or before a final output generation. That node structure gives you precise points to inject compression logic.
Makes sense. And finally, isolating context in LangGraph.
For isolating context, that central state object we mentioned, you can define a specific schema for it. By having distinct fields in your state schema, you can store context from different sources, tool calls, user input, memory, in their designated spots, effectively isolating them until a node explicitly needs to access a specific field.
The compartmentalization again.
Exactly. LangGraph also explicitly supports integrating with those sandbox environments like E2B or Pyodide. So you can have a node that calls out to a sandbox for execution, isolates that computation, and then only brings back a controlled piece of context into the main graph state. It even supports persisting state within those sandboxes across turns if needed.
Powerful.
And lastly, for multi-agent architectures, LangGraph has extensive support. There are libraries and patterns specifically for building supervisor agents that coordinate subagents or even agent swarms. It makes managing the isolated context and communication flows for multiple agents much more structured.
Wow. Okay, what an incredible deep dive into context engineering. It's clear how it moves so far beyond just writing clever prompts. It really is this delicate art and science, like Karpathy said, of curating the AI's entire working memory, from writing and selecting to compressing and isolating. These strategies seem absolutely fundamental if you want to build effective, reliable AI agents.
Absolutely. And seeing how frameworks like LangGraph and tools like Langsmith are evolving specifically to tackle these challenges is really encouraging. They're making these advanced techniques more accessible, giving engineers the kind of granular control and, crucially, the observability they need to actually master this craft. It really does feel like it's becoming, or maybe already is, the number one job for engineers building sophisticated AI agents.
So thinking about everything we've covered, what really stands out to you from this deep dive? As you listen, think about how these principles, writing, selecting, compressing, isolating, might apply to maybe an AI assistant you use every day, or perhaps that advanced agent you're dreaming of building.
Yeah, and if we try to connect this to the bigger picture, even though context engineering is a relatively new term, the underlying practices, the need to manage this limited working memory have been evolving super rapidly alongside the models themselves. It's just not about optimizing a single prompt in isolation anymore. It's really shifted towards architecting these dynamic systems that ensure the LLM has everything it needs to succeed.
But only what it needs.
Exactly, and only what it needs at the precise moment it needs it. That's the art and science part.
Which leaves us with a fascinating question, doesn't it? In this world of increasing AI complexity, where we're hearing that agent failures are often actually context failures rather than fundamental model failures, how might the automation of context engineering itself become the next big frontier? Could we see AI systems that learn to manage their own context more effectively, maybe refining these strategies, writing, selecting, compressing, isolating in real time based on the task? Something for you to mull on as you continue your learning journey. Thank you so much for joining us on this deep dive into context engineering. Until next time, keep digging for those insights.